Thank you for the introduction. Good afternoon. My name is Saurabh Kadekodi, and I'm here to talk about Tiger, which is disk adaptive redundancy without placement restrictions. This is in collaboration with my colleagues from CMU and Google. And Francisco Maturana is actually here, so you can catch him and talk to him if you have more questions also. So this is part of a larger body of work called disk adaptive redundancy, or DARE. So before I go into the talk, there's one really important thing I need to tell you, so I need all of your attention, which is no tigers were harmed in the making of this presentation. Okay, so now that I have your attention, I'm going to tell you about our awesome system. So our system Tiger is in the context of large scale storage clusters. So today, hundreds of thousands of hard disk drives make up the primary storage tier. And at such scales, failures are extremely common. And disk failures are typically measured in terms of annualized failure rates, or AFR, which is nothing but the expected percentage of disk failures in a given year. So our previous analysis has shown that AFR varies heavily across different makes and models. So we saw over 5.3 million disks that were deployed in production environments at NetApp, Google, and Backblaze. And there was over 100x difference between the weakest and the strongest disk. So each box here represents disks belonging to a single make model, at least 10,000 of them. Okay. And on the y-axis, you have AFR plotted on log scale. Okay. So AFR highly varies across makes and models, but also AFR varies across a disk's age. And I'm showing this using the typically used bathtub curve or hazard curve, which has higher rate of AFR during infancy and wear out, and a low failure rate during its useful life. So now that AFR varies across makes, models, and across age, let's take a look at how the AFR heterogeneity impacts the reliability. To do that, let me first give a primer on erasure coding, because that's the most commonly used technique to obtain reliability. So in erasure coding, you have data which is chunked up into equal sized pieces, and any k of these data chunks are paired up with n minus k parity chunks to form an n chunk stripe. An n chunk stripe can recover from up to n minus k failures. In this example, I have a 3 of 5 stripe which has 3 data chunks, 2 parity chunks, and it can recover from 2 data losses, 2 losses of any 2 chunks. Okay. So now in a typical cluster, you will have a mix of makes and models and of ages. Here, when you exercise a certain level of reliability using a redundancy scheme, say 6 of 9, what ends up happening is these 2 stripes end up having different reliability because they are stored on differently reliable disks. In this case, because the yellow disks are the least reliable and the blue disks are medium and the strongest are the green disks in this toy example, the top stripe is actually less reliable compared to the bottom stripe because it has many more yellow disks as a part of its stripe. Okay? So the same level of redundancy is either insufficient, or what happens more often than not is overly wasteful because cluster administrators are conservative in selecting their redundancy schemes that they use on these disks. So the concept of disk adaptive redundancy is to differentiate between the different bathtub curves of the differently reliable disks and remove excess redundancy in a safe manner, and therefore reduce the overprotection that usually happens, which leads to lower storage costs and lower energy costs. Okay? All of this is done while being extremely safe that no data ever misses the target reliability that is required. Now, the state of the art system before Tiger, Pacemaker, the way it achieved disk adaptive redundancy was to first logically group disks that belong to a certain failure rate, and we call Pacemaker called them redundancy groups, or R groups, and stripes were laid out entirely within an R group. Now, which scheme was used in an R group was dependent on the observed failure rate of that particular R group. So in this case, you see that the narrowest stripe with the highest redundancy is in group yellow, which has the weakest disks, and the widest stripe with least redundancy is in the green set of disks, which has a lower AFR. Okay. Pacemaker was designed to perform disk adaptive redundancy with minimum I/O overhead. And the I/O is required because disks change their AFRs over time, and you may need to re-encode the data to keep it safe. Now, Pacemaker had some problems with respect to its adoption in practice. The first problem is it enforces an additional placement constraint. So, stripe allocation is already a highly constrained algorithm. So, two chunks of a stripe can't be on the same disk. They cannot be even on disks in the same servers or racks. They have to be across fault domains, etc. So, there are already a lot of constraints that need to be handled before you allocate a stripe. Pacemaker added a constraint of putting stripes within R groups, and this additional constraint can potentially be crippling. Secondly, Pacemaker also results in low risk diversity. So, by risk diversity, we mean when you lay out a stripe, what is the number of unique makes and models that are covered by chunks in a stripe. So, Pacemaker forces disks to be in a certain R group, and R groups are highly correlated with makes and models. And so, what ends up happening, as seen in these two clusters, is that for a variety of scheme configurations, you actually get very little risk diversity, because most chunks end up on disks of the same make model, or otherwise only a handful of make models that are there in the cluster. So, here both Backblaze and the Google cluster on which we simulated showed really low risk diversity, where ideally you would like to be as high as possible. Finally, Pacemaker has an all or nothing approach to performing disk adaptive redundancy. So, today redundancy is enforced at a stripe or file granularity, whereas Pacemaker is designed from a disk centric perspective, where adaptive redundancy is designed from a disk at a disk granularity. So, whenever a disk's AFR changes, you need to re-encode all of its chunks, even if the data on those chunks actually did not want to participate in disk adaptive redundancy. So, no partial adoption is possible when using Pacemaker. Either the entire cluster has to commit to performing DARE or none of it. So, to solve these problems, we came up with a new system called Tiger, which performs disk adaptive redundancy without placement constraints. And it does this by the help of two primitives, eclectic stripes and eclectic volumes. And I'll go ahead and explain what these mean. So, first let's look at homogeneous stripes. Today, when there is no disk adaptive redundancy at all disks are assumed to fail at the same failure rate. So, if you have 2 6 of 9 stripes, they provide the same reliability because they are essentially residing on disks that are assumed to fail similarly. In Pacemaker, you differentiate the different R groups, and if you have 2 6 of 9 on 2 different stripes on different R groups, you actually do get different reliability, but that comes at the cost of having a placement restriction. With eclectic stripes, you use the same allocation algorithm as that of the homogeneous stripes, but now by being able to calculate the reliability accurately by taking into account the AFR heterogeneity within each stripe, eclectic stripes also can result in different reliability in 2 6 of 9 stripes based on exactly which disks are participating in that stripe. So, let us look at how the reliability is calculated for eclectic stripes. So, we use the commonly used mean time to data loss to calculate the reliability. In the conventional setting, we would have a Markov chain that looks something like this, where the states represent the number of simultaneously failed chunks in a stripe, and DL is the state where you have permanent data loss. And this is how you would solve this Markov chain to go from time it takes to go from 0 to DL, which is MTTDL. Now, when you take AFR cognizance into account, the same Markov chain can look something like this. There is a state space explosion because now which disks fail actually matter. And here calculating the exact MTTDL can be prohibitively expensive. Now, one assumption that we make comes to our rescue, which holds true in practice and allows us to have a very simple approximation for calculating this really complicated MTTDL. So, whenever the repair rate is much higher than the failure rate, which is true in practice, we have a very simple approximation that is highly accurate. It provides over 95% accuracy of an exact MTTDL, and on average over 99.5% accurate, and importantly it is simple and fast. But most importantly, it is a closed form formula that allows us to interpret the reliability given by eclectic stripes much better. We can also conduct what if experiments to understand what would happen to the reliability if I were to switch out these two low AFR disks with high AFR disks and so on. Okay. Now, let us look at how the MTTDL compares across the different striping techniques. So, in this plot we have the MTTDL on the x axis, and I am going to talk about the different striping mechanisms on the y axis. So, when you have homogeneous stripes assuming an average AFR for the whole cluster, we see that some of the stripes are indeed underprotected. So, the black line in the center is showing the target reliability you want to always meet. So, some stripes end up being under reliable. Most often than not, cluster administrators assume the reliability of all disks, the AFR, to be the max AFR that they have ever observed, in which case all the stripes are sufficiently protected, but actually are much more overprotected. This is costly. With Pacemaker, you have groups of stripes because of the different R groups, which is seen in these clusters, but there are still some clusters which are to the right, which are wasteful. With eclectic stripes, you have all stripes that are adequately reliable, and at the same time they have minimum storage overhead compared to the other striping mechanisms. So, let us take a look at eclectic volumes now. Today's terabyte sized disks have megabytes, today's disks are terabyte sized, but the chunks in a stripe are in the order of megabytes. So, whenever a disk's AFR changes, you need to quickly identify which stripes might require change by looking up their reliability. Eclectic volumes are a collection of eclectic stripes on the same disks. So, each disk has a mapping from volume ID to stripe ID, and essentially terabyte sized volumes can account for the reliability of millions of stripes. So, whenever the AFR changes, by only looking at a handful of eclectic volumes of reliability of a handful of volumes, we can guarantee the safety of millions of stripes without having to enumerate them one by one. So, in our system, let me explain how these components work. So, we have the eclectic stripe allocator, and the key takeaway here is that it sits beside the conventional allocator and uses the same placement policy that is in your cluster today. The eclectic volume manager is responsible for the creation and deletion of eclectic volumes and also maintains metadata about the volumes. And the eclectic stripe manager is responsible for the computation and safety of eclectic stripes and of the stripe manipulations whenever the AFR changes. So, the interaction between these components and how they fit into the system as a whole, the details are in our paper. Okay, so let us look at some evaluation. One of the important things that Pacemaker provided was space savings, because it reduced the heavy overprotection that was going on in homogeneous stripes. So, we see with Tiger that Tiger matches or even exceeds the space savings that are provided by Pacemaker. So, here we have 4 clusters on the x axis, 1 Backblaze and 3 of the Google clusters, and on the y axis you have the overall space savings by using disk adaptive redundancy in Tiger and Pacemaker. And we see that we can get up to 20% storage space savings. Now, in clusters with hundreds of thousands of disks, this is a sizable saving. At the same time, we also need some I/O in order to manipulate eclectic stripes to ensure that they are adequately reliable. The I/O footprint of Tiger is extremely low. It is at most 0.5% of the cluster's I/O bandwidth, essentially meaning that it is in the noise. Looking at risk diversity, if you remember, Pacemaker had low risk diversity because of the R group restriction. In contrast, Tiger, shown using the orange line, has a much higher risk diversity, at least 60% across all schemes that we saw, and could cover many more makes and models when it's striped, because it was picking disks at random according to the current allocation algorithm. Another advantage of Tiger is that it is robust to increases of AFR in any one make model. So, you might have makes or models that see manufacturing defects and might lead to bulk failures. At such times, systems such as Pacemaker are actually vulnerable, because a small increase in the AFR of all disks of a make model would increase the I/O required to re-encode by quite a bit and might overwhelm the system. And that is what is shown here. A minor increase in a single make model caused Pacemaker to have a huge I/O burst, because it had to re-encode all the stripes in that R group, essentially all data on all disks of that make model. Whereas for Tiger, because only a very few chunks resided on disks that were failing, Tiger need not have to do that much I/O in order to make up for those bulk failures. So, Tiger is more robust to sudden AFR rises. So, in conclusion, Tiger provides disk adaptive redundancy without placement restrictions. It provides significant space savings, saving millions of dollars at very low I/O overhead, and it performs disk adaptive redundancy at the stripe or file level, which adheres to the current way in which redundancy is enforced. All in all, Tiger makes disk adaptive redundancy much more practical. Thank you.